In this short vodcast, we're going to use this worksheet that you can see here to show you how simple it is to use volume ratios in a gas laws equation and also the molar volume of a gas to do what we call gas stoichiometry. So first off, please go find this page in your packet. Please be very careful. There's a page that has two sides that look identical. You want the side that says 30.0 liters of acetylene gas. Take a moment to go find that. You're going to need a calculator, and if you have access to a periodic table, you can confirm the calculations that I've made. So now that you've picked up your periodic table, your calculator, and your correct worksheet, the first reaction anyone would have would be to make sure that the equation is balanced. So in this first solution, you can see that I've balanced, and we have 2 moles of acetylene, that's the C2H2, requires 5 moles of oxygen to produce 4 moles of carbon dioxide and 2 moles of water. Now here's the really cool thing. If you look carefully at the problem, you'll see that all of them are gases. And you'll also see that we're at STP, standard temperature and pressure. So there's something pretty cool about gases. You can now substitute any unit of volume that you wish instead of the word mole to represent the relationships on a volume basis. So 2 liters of acetylene and 5 liters of oxygen produce 4 liters of CO2 and 2 liters of water. I could have substituted in milliliters, but that'd be a pretty small reaction to try to keep track of. So what we're doing now is something that looks like a mole-mole problem, except it's a liter-to-liter problem. If the problem starts with, on question number 1, 30 liters of acetylene and asks for liters of oxygen, go get the ratio of liters of oxygen to liters of acetylene in the balance equation, just like you did with a mole-mole problem. So 30 times 5 over 2, which is 2.5. In my mind, that's going to be 60 plus 15. If you had to reach for your calculator, no problem. And express it to 3 sig figs. 75.0 liters of oxygen would be required. By the way, acetylene, C2H2, is an important gas that we use in welding. And of course, welding is the way that we bond 2 different parts of metal to each other in a very strong and hopefully permanent fashion, unlike the Bay Bridge in San Francisco. Okay, next problem says, how many liters of carbon dioxide are formed? Well, this time the relationship is between acetylene and CO2. And it's 4 liters of CO2 for every 2 liters of acetylene. In my mind's eye, that's the number 2, and 2 times 30 is 60 liters of CO2 would be produced. Remember, this is a combustion reaction, so the burning of any hydrocarbon, the acetylene, and oxygen will produce CO2 and water if the combustion is complete. Question 3 asks, now let's take that 60 liters of carbon dioxide from the previous problem and turn it into moles. Here's the other cool part about gases. 1 mole of any gas occupies 22.4 liters of space. And that's where this guy came from, the molar volume. So if you're ever given liters and they want moles of a gas, or if they've given you moles and they want liters, and you know you're at STP, just divide or multiply by the 22.4. So 60 liters of CO2 is really 2.68 moles of CO2. Important concept. That could have been 60 liters of any gas. Remember, at STP, the volume of any gas, 1 mole of any gas, is 22.4 liters. The identity of the gas does not matter. Question number 4 is now going to walk us through a 3-part problem. And depending upon how your brain likes to process, you can do this in a stepwise fashion like I've done on this worksheet, or you can do it in an elegant stoichiometric calculation, which I'll show you on the last slide. So if I'm asked how many liters of water are produced, start with your 30 liters of acetylene again. This time the ratio is dead simple. 2 liters of water produced for every 2 liters of acetylene. That's a 1-to-1 ratio, so 30 liters of acetylene cranks out 30 liters of water vapor. Problem 5 requires that you turn 30 liters of water vapor into moles. Once again, use the molar volume. 1 mole of water vapor occupies 22.4 liters of space. So essentially you divide 30 by 22.4 and we get 1.34 moles of water vapor. Finally, if I ask you to take moles of water and convert that into grams, reach for a periodic table. I rounded off here, so I'm cheating a little bit. 1.34 moles of water times 18 grams and 1 mole of water. That means that if I burn that amount of acetylene, I'd make 24.1 grams of water vapor, which of course you could cool down and condense into a liquid and weigh if you wanted to. So finally, questions 4, 5, and 6 can really more easily be combined in one elegant stoichiometric calculation. It looks kind of like a mass-to-mass problem, doesn't it? Except we're going to take liters of acetylene and turn it into grams. And we start with what we were given, our 30 liters of acetylene. I solve for, in the first conversion factor, liters of water by using the molar ratio. In the next conversion factor, I turn liters of water into moles by dividing by 22.4. And in the third conversion factor, I turn moles into grams by multiplying by the molar mass. If you're ever in this situation, always start with what you know, liters of C2H2, and at the top of the last bar, oops, I should have written the word water there, I need to solve for grams of water. It'll become pretty apparent to you that you'll be using the molar ratio, the molar volume of a gas, 22.4 liters in 1 mole, and the volume to volume ratio that comes from the balanced equation. So you'll see a number of other problems that look like this, but this is how gas stoichiometry problems work. If you have a basic understanding of regular stoichiometry, then you're going to find this part of the chapter quite easy. Take care until the next time.